Hello, welcome to lecture 3. In this lecture, we'll learn more about different types of the learning problem. In the previous lecture, we have seen a simple algorithm called perceptron, and that it can be used for problems that require binary answer, such as approving the credit card, generating outputs yes and no. So we have also seen that the perceptron learning algorithm is based on linear separable data. Also, it uses a class of functions called perceptrons to get the hypothesis G that we are interested in. So in this lecture, we will further move on and study different settings of the machine learning task with different output spaces, different data label, different protocols, and different input spaces. Let us revisit the credit approval problem that we have seen earlier. The task here consists of training a learning algorithm that would give us binary output. In this case, approve or deny credit on the basis of some information about the applicant. We have here, for reference, our different components of our flowchart. We are still interested in finding this unknown target function that takes the input data and ideally knows the answer yes and then no. The y is here denoted as output. So the training examples is the collection of historical records in the bank. X1 vector could correspond to the information from one applicant. Y's here are scalar values. They are either one of these, -1 or plus, okay? And our learning algorithm takes this data, or pairs of the data, we also call them as training example, and updates, learns from this data and selects one of the candidate perceptron in the previous example and declares it as G. So if this is our perceptron learning algorithm with a simple weight update rule, these are the set of perceptron hypotheses, right? And finally select the G that makes no mistakes on the given input training example will provide us automatic approval of a credit card application or denial. Right? And we formally call these kind of problems in machine learning as a binary classification task because the output involves only binary output. And also this kind of problem is called as supervised learning. Let's take a look at more binary classification problems. For instance, we have already seen credit card or credit application approval or disapproval problem, right? The output involves binary outputs. Well, we may also have data corresponding to a bunch of emails, and our algorithm or machine learning algorithm may be tasked to identify spam versus non-spam emails. We also have data from patients recorded in hospitals or any kind of data that correspond to patients' state of being. And then the algorithm tries to classify into sick and non-sick. Or may also have some data from ads, advertisement. In these specific cases, we may be interested in learning a function to identify whether the ads or the data from that shows profit or not profit. So profitable or not profitable. Also involves two binary class. Also, we may also have a bunch of student answers to some exam problems or quizzes. And we can train a learning algorithm to automatically check these answers and identify correct or incorrectness. Well, binary classifications are considered as a core and important problem in machine learning. And many of the tools are initially formulated for binary classification problems in machine learning. We can see like we are interested in finding this hypothesis that separates, for instance, good from bad. So this could be approve, and this could correspond to the disapprove or deny credit application region. And also similarly here we see. So binary classification tasks involve finding one decision boundary that separates into two classes. Multiclass classification is further extension to binary classification. Let's present this example using a coin recognition task. Okay, given bunch of coins that represent 1 cent, 5 cent, 10, 25, also called as pennies, nickels, dimes, and quarters, represented by two features: size and then the mass. We can imagine that the quarter, 25 cent, will have bigger size, also the mass. So if you take a look at the scatter plot of these two features in 2 dimensions, we can see them here. And we can label them by using our Y as 1 cent, 5 cent, 10, and 25 cent. Or more abstractly, we can just give them some number. 1 cent, 2, 5 cent represents 5 cents, 3 could represent 10 cents, and 4 to 25. Well, it can range up to K-class problem. In the binary classification case, we had the K equal to 1. So we have 1 and 2, or plus or minus. Deciding the Y, how they should appear, is up to you. Usually, in multi-class classification, we have 1, 2, 3, 4, 5, 6. In binary classification, we can see Y to be like 0 and 1, or minus 1, plus 1, or rarely 1 and 2. Okay, so in multi-class data collected from 4 different classes. The color here corresponds to, again, to the label. Right? Manually, we could label them as, right, these, all the coins you see here have their own label. So this one, we can decide to label them as Y1, Y is 2, Y is 4, Y is 3. Once we have our G learned from these given dates, the task of the G will be given some new data, let me call it new data, without any label. The G should be able to identify 1 of 4. So among 1, 2, 3, or 4. We can see some other multi-class classification problems. For instance, we have handwritten digit recognition problem, where the learning algorithm tries to recognize the digits automatically. Yeah, and also other examples include, we have pictures of different apples, orange and strawberry. The task of our machine learning function hypothesis will be to, given any picture, identify whether it is apple, orange, or strawberry. Well, we also have another example. So from spam to non-spam, from binary to multi-class extension. Usually you see in your Google Gmail, we have emails that are automatically categorized into spam, primary, social, promotion, and update. More widely known tasks involve multi-class classification task in machine learning. Another type of machine learning problem is called regression. Okay, let's take a look at this patient recovery prediction problem. You have some data from patient that represent the health status of the patient. So with the binary classification, you can solve or sick or not problem. So you take the input data and then train an algorithm, train your hypothesis, and then come up with a function that will give you a sick or not answer. In multi-class classification problem, you can use these features, the data from the patient, and then learn how to identify which type of cancer, okay, the patient has. While in regression, we can take same patient features or the data from the patient and ask different questions. For instance, how many days before recovery? Or we can try to predict how soon the patient is going to recover. So the number of days could be 1 day, 2 day, 100 days, even more, right? So this is kind of even more extended version of multi-class classification. But here the output y is any real valued. Okay, so we have some lower bound and upper bound. In this case, lower bound could be 1 day, upper bound. And the regression problems are usually deeply studied in statistics. So okay, in binary we have y to be plus minus 1. In multi-class classification, y depends on the number of classes. If we are interested in identifying 4 different types of cancer, then y will be limited to 1, 2, 3, 4. While in regression, it could be any real valued number or integer. So other type of problems, let's say we have some data from the company, and then using that data we can try to estimate the stock price, and the price also range from 0 to millions, hundreds of thousands. Or climate data. So based on the climate data we can try to predict the temperature of tomorrow, or the weather forecast. So regression problems, also core and very important problems in machine learning. So if we summarize, we have seen 3 different types of learning with different output space. First one was a binary classification one, which involved the binary output, usually denoted by minus or plus 1, and can be used for simple tasks such as given data from a customer or applicant who is applying for credit card. We're just interested in yes and no answer, approve or deny. Well, further, we have also seen multi-class classification task where the output consists of up to k classes. So one of the example could be handwritten digit recognition. The k could range to up to 10 classes. And we briefly discussed the regression, where y, the output space, is any real valid number. In fact, lots of practical problems are well described as regression problems. For example, predicting the rating that the user will assign to a movie can be thought of as a regression problem. And usually, if you have some problem that involves asking questions such as how much, how many, then all these problems involve regression. How many days are left before patient recovery? How many hours will this surgery take? So R could go from 1 to several hours. Or give an image of some dogs, you may ask, how many dogs are there in this image? While in binary, you may be involved, like given image of data, image of dogs, you ask, does this image contain dogs or not? Here, regression, how many dogs in this image? So our learning flowchart may say we have a known target, and we have seen different possibilities of having y. Y could be binary, multiple, multi-class, or it could basically be R. A model, same problem, only the difference is we have different output space and same goal. So most of the algorithms are defined initially as a binary classification and can be extended to multi-class problems, and also the regression. Now, let's take a look at this quiz based on what we have seen so far. What is this learning problem? The entrance system of the school gym which does automatic face recognition based on machine learning, is built to charge for the different groups of users, different staff, let me highlight, staff, student, professor, and others. So what type of learning best fits the need of the system? Is this a binary classification problem or multi-class classification? Is this a regression or structured learning? Okay, we didn't cover this, but among these three, binary, multi-class, or regression, the answer is obvious, right? It is a multi-class classification problem because we have explicit Y that contains 4 classes. We want to classify the image, face image into staff, student, professor, or other. Okay, let us further clarify different learning scenarios with different labels. First, let's take a look at so-called supervised learning and take the example of coin recognition problem. So in supervised learning problems, we have a data, each having corresponding Y labels. Okay, every xn comes with corresponding Y. If we imagine this x1 represents one of these coins, then y1 will represent the color. Okay, x2, this coin and color would represent 1 cent, 5 or 25 cents. This is a multi-class, 4-class classification problem. So the person who collected this data and who measured mass and the size of each coin provided us also with the labels. Okay, so that we can use those training examples, those training data set in our machine learning task. So these kind of problems are called supervised learning. To clarify more, let me open the perceptron learning algorithm that we have seen in the previous lecture. So, why it's called supervised? So in supervised learning, we said every x example comes with y. This is vector, this is scalar. Well, it is, and also this step is very important. Well, this step is important because that leads to the decision of whether we need to update the weight or not. Well, given some current weight and an example and its sign, whether the sign is plus minus 1. So this y is given by the teacher. Let's put that in that context. So the teacher, okay, is comparing your answer with the correct answer and telling you, hey, you need to update. This is a wrong hypothesis, right? If you didn't have this y provided in our training data set, then it would be impossible to check and we need to update our weights or not. It's called again supervised because we have the current example, the hypothesis selected by algorithm, and correct answer provided by the. It is called supervised learning. In contrast, in unsupervised learning task, our data set doesn't come with y's. So in supervised multi-class classification case example, we had different coins. Each of them is colored. The coloring means the y labels. Data with some features, size and mass, we don't have y's. The task will be to identify some clustering, some groups. We can call also this as cluster. Unsupervised multi-class classification problem. The task is to identify these kind of clusters automatically based on some metric. Okay? While in supervised case, we know we can calculate error, measure, and thus update the weights and make sure that the hypothesis is correct or not. While in unsupervised case, it's a little bit more challenging because we don't know exactly whether these points, examples belong to this specific group. There are many interesting problems related to unsupervised learning. For instance, you have a bunch of news articles downloaded from the web, and you may try to identify the topics of those articles. But those articles do not come with whys, so you may cluster them according to the themes, topics, such as news articles belonging to politics, science, or entertainment, or many other topics. We can give some more examples. So, other unsupervised learning problems. So, clustering, we have input data, cluster them into some groups of data points, again, from articles to topics. Since we don't know how many possible topics we can have, we can manually set it as unsupervised multi-class classification, or unsupervised, let's say 4 or 5 class classification, or some density estimation. You have some data. So in this case, for instance, if you have data from traffic with a location, right, which contains, for instance, car accident cases, or some other interesting information, you may try to use those data set and try to identify dangerous areas in the city. Or in outlier detection example, you have some data without y, just some data, and your task is to identify some unusual examples. Internet logs. From internet logs to intrusion alert. For instance, it happened to me that if I log in, if I lived in Kazakhstan for many months and used my Gmail there, and if I go to US and then try to log in, it may give some alert saying that, okay, this is some unusual behavior, unusual login. I'm just making sure this is you. So another interesting problem is called semi-supervised learning. Well, here we have the same coin recognition problem, but with some or partial whys. So if we take a look at supervised case, in supervised we have all the coin examples labeled. All of them have corresponding whys. While semi-supervised case, only partial data is labeled, okay? Or 10% of the data for each class is labeled, and the task is to use those partial information, partial label, to perform classification task. While in unsupervised case, if you compare these three, we have no labels at all. In semi-supervised, we have some labels. You might have seen Facebook has this face identifier. It learns from your images, okay, in your profile, and when someone posts the image of you, tries to recommend you some labels. Semi-supervised learning is useful, okay, and can reduce the task of manual labeling or manual labeling of huge amount of data set. Let's take a look at different type of learning problem, which is called reinforcement learning. It's a very similar to natural way of human learning, and it's different from the learning task we have discussed so far. Let's say that you have a dog and you want to teach it to sit down. You say to your dog, sit down. Okay, this is a kind of iterative procedure. However, the dog pees on the ground, and then you get angry and then you say, bad dog, very wrong action. Pee is wrong. So in this situation, it's very hard to show your dog the why that you expect is sit, okay, when x is input data is sit down. However, you can give some y tilde another kind of output as a punishment to say p is wrong. Well, in your next attempt, you say sit down, the dog sits down, your response will be very positive. Good dog. You will praise, okay, praise it. And let me give you some cookies. So even in this situation, still it's hard to show that y is sit, okay, when the x is sit down, but you can reward, you can provide some kind of y, okay, meaning that sit is good. So in reinforcement learning, we have x, okay, the data that we want to show, and then y, expected. Usually we have these triplets, so x, y tilde, and then goodness. Some other example of reinforcement learning include the customer ad choice, ad click earning in advertisement system, and some blackjack agent game. In general, this kind of learning learns with a partial implicit information, and usually sequentially. So data comes one by one. In supervised learning, we have all y's available. So we have n data points, for example, training examples. Each has corresponding y. Y could be just binary value or multiclass or some real valued number, integer for regression. In unsupervised case, we have data without y. Right? Unsupervised is also known as a clustering problem. Further, we discussed briefly about semi-supervised, where we have data, training examples, but only some of them are labeled. Not all of them have labels. Why? Because usually when you collect data, the labeling process is very time-consuming. So semi-supervised learning tries to address the problem that given some part of the data set with labels, can we use those y's to generalize to other data sets? And fourth, we have seen reinforcement learning problem, which was very similar to how we learn. It's a sequential learning problem, is based on implicit y, implicit output, some goodness measure. So in this course, we will be mainly focused on supervised learning problems, also cover some unsupervised, semi-supervised, but reinforcement learning requires entire different course, so we won't be seeing examples of reinforcement. So in our flowchart, we have data and three cases: data with y, no labels, no target values, and some target values. Our learning model, final hypothesis, our goal remains same. We want to find g that approximates our target function. Let's take a look at this quiz and try to answer what is this learning problem. Well, here, to build a tree recognition system, a company decides to gather 1 million of pictures on internet. Then it asks each of 10 company members to view 100 pictures and record whether each picture contains a tree. The pictures and records are then fed to a learning algorithm to build a system. Now, what type of learning problem does the algorithm need to solve in this case? Just pause the video for a minute and then try to select the correct answer, whether this is supervised, unsupervised, semi-supervised, or reinforcement learning. Okay, so we can focus on data sets. So 1 million, so we have 1 million pictures on the internet. 10 pictures and record whether each picture contains a tree. Well, this is a clearly semi-supervised learning. Only 1,000 records are labeled with the corresponding Y. Okay, the other remaining 999,000 pictures are unlabeled. So you can now again think about the amount of the time you may spend if you decide to label all of the million examples of pictures. It may be very laborious or time consuming. Now let's talk about different learning protocols. First comes example of batch learning. Well, batch learning is just learning from all known data. For example, you have coin recognition problem and you collected thousands examples of coin. The batch learning just takes all the thousands of examples of the coin and learns from it. Learning means the learning algorithm selects a hypothesis G. So we use all those 1,000 examples of the coins. Okay, so it is called as, we can call this as batch supervised multi-class classification. So we learn at once from all known data. For example, batch of email and spam. To design spam filter, healthy patient data, cancer patient data. And try to come up with a cancer classifier. We use batch of all patient data and then group of patients. So basically batch learning is a very common protocol in machine learning. So that again involves learning from all known data sets. Another protocol of learning is called online learning. To understand this better, we can take a look at the spam filter that improves over time. So in batch case or batch spam filter case, we'll learn from all emails and then spam examples, right? And then try to predict, try to learn the G and then use with fixed G. Okay, these are functions. This is batch. So if you have a million examples of email and spam, you learn from, you use all of these examples and then fix a G and then use it in your decision making or as a spam classifier or filter. While online learning is different from batch one in the sense that the learning occurs sequentially. So the input data comes one by one. So in batch case we use millions of examples or all batch data, but in online case it is sequential. So we observe one email, predicts whether this email spam or not, okay, with the current G, weight, and then desired label, receive the desired label from user, and then update G with X and Y. Right? This is the example of online learning. So we learn from one example at a time. You may have some situations where your email or important email ended up in your spam folder. And then you go to your spam folder and then provide the correct label. And you say, this is not a spam. That is one of the simple examples of online learning. And then the G will update its weights. So we can think that perceptual learning algorithm can be easily adapted to online protocol. How? Just take a moment and think. Can it be? Yes. And reinforcement learning is, yes, done online. Why? Why do you think so? So, usually online learning involves selecting the hypothesis from sequential input data. We don't have batch of input training example, we have one by one sequential available data. And then, selecting the final G involves a lot of sequential information and then some Y from the user. Another type of learning is called active learning. Active learning is very similar to online learning, but with some active involvement of the users. In this protocol, first let's take a look at batch learning. Batch learning is just kind of duck feeding. So you just take all the data set and then learn from it. Your G is selected based on the entire data set. Online learning can be considered as a passive way of sequential learning. You have one by one data set, and then you update your weight based on the user input. In active case, it's extension of online learning. It involves one more step of question asking. Also, sequential learning involves like query of Y of the chosen egg. So in active learning, the output is provided, and then you ask the user whether this output is correct or not. And in active learning, the improvement is based on strategic question asking with fewer labels, hopefully. And in our flowchart, we have this arrow going to unknown target function. Depending on the type of the strategy you select in active learning, you can ask questions related to unknown target function. So if we summarize and compare all of three protocols, we have batch learning, which involves learning from all collected data, online type of learning protocol that involves learning from sequential data, and active. So active learning is a very interesting area of research. However, most of the learning protocol is based on batch learning in real world. What is this learning problem? A photographer has 1,000 pictures, each containing one baseball player. He wants to automatically categorize the pictures by its player inside. He starts by categorizing 1,000 pictures by himself, and then writes a simple algorithm that tries to categorize the other pictures if it is confident on the category while pausing for learning from human input. If not, what protocol best describes the nature of this algorithm? Is it batch or online? Is it active, random? In batch case, we need to learn from entire collected data at once. In online case, we have sequential data. In active case, we also have sequential data, but with strategic question asking step added. Well, 4 could be random. So as you can guess, this is an active learning protocol because it pauses for human input. It asks question if it is confident or not, right? So the algorithm takes an active but naive strategy and asks when confused, right? In the final section of this lecture, I just want to quickly go through different input feature space possibilities. Okay, in the definition of features. Well, let's take a look again at credit approval problem. So we have the applicant information with age, gender, salary, and some other information. And these are flowchart. In this case, these specific features represent concrete features. So 23 is one of the features, female another, salary another, year in residence another concrete feature. We treat them as a concrete feature. So because each dimension of our X represents a sophisticated physical meaning. It has sophisticated physical meaning. For instance, the concrete features, as we have already seen, can be the size or mass in the coin classification problem. Yes, they have some physical meaning, right? Sophisticated is physical meaning. Customer info for credit approval also have, or patient info for cancer diagnosis, often includes including human intelligence and learned that. So concrete features usually such as height, weight, or age, salary, are easy tasks to work with in machine learning because they're concretely defined and they can be associated with some physical meaning, some sophisticated physical meaning. So to understand the concrete features, we can compare them as raw features. So raw features, in contrast, can be the picture elements or pixels in digit recognition tasks. So here we have some grayscale images corresponding to handwritten digits from human, so 1, 0, 1, 3, and our vector x usually consists of the all concatenated pixels. We will have these pixel values as raw features. And then task here is again to recognize whether this is 4 or 8 or 7 using a machine learning algorithm. And these features related to the pixels or picture elements represent the grayscale that usually range from 0 to 255, 255 meaning the black represent the picture elements or raw features. So we can, for instance, compare raw versus concrete. So we can generate concrete features out of the raw features by extracting some features, for instance, symmetry and density of each handwritten digit. Okay, so we can extract these features from raw features, where raw features, for instance, in 16 by 16 gray image we have, okay, this is normalized values that range between 0 to 1, corresponding to brightness into concrete features. Okay, so symmetry. For instance, 1 is symmetric, too much, very symmetric. Density, usually the density of the dark areas here. Okay, so we see that 5 is more dense, 1 is more symmetric. However, this one can be a bit confusing. So usually raw features represent simple physical meaning. Okay, it is more difficult than concrete features in machine learning. And also raw features can appear as image pixels, speech signal, amplitude values, and usually raw features require human manual feature extraction to extract some useful concrete features. Another type of feature is called abstract features. To understand this better, we can take a look at rating prediction problem, where what we have here is user ID, item ID, and rating. The task is to predict the rating that some user ID would give to item ID. This problem is a regression problem where output y could range any real valid output as rating, which consists of user ID and item ID. So the input x, because it consists of ID, it's very hard to associate it with any kind of physical meaning, right? The IDs are very abstract, so it's very hard to get some physical meaning. Therefore, it's very hard to deal with in machine learning tasks. We can think of concrete features as the easiest feature type in machine learning, as they correspond or they can represent sophisticated physical meaning, while raw features with simple physical meaning requires one more step of feature extraction, feature conversion. The abstract feature types are most difficult ones in the machine learning. If you have data set with abstract features, you usually again work on feature extraction, conversion to extract usually or construct the dataset with concrete feature types. Let's take a look at this quiz quickly. What features can be used in this case? We consider a problem of building an online image advertisement system that shows the users the most relevant images. What features can you choose to use in this case? Is it concrete, concrete raw, concrete abstract, concrete raw, or abstract? So which one of them will be the relevant feature? So the answer is 4. The concrete user features. You also want to use raw input image features and some abstract user image IDs. So let me quickly summarize this lecture. So in this lecture we have discussed different types of learning. We have seen simply the problem of classification and regression. And also we have seen an example of a supervised, unsupervised, or semi-supervised learning task. Also briefly mentioned about reinforcement learning. We've seen different learning protocols we call batch, online, and active. And we mentioned that batch learning protocol is widely used in machine learning. And also we briefly reviewed different input space, different input feature types, where we mentioned that concrete features are the easiest ones to deal with, which has sophisticated physical meaning.